Okay, now we will continue with the system properties, some very basic properties I will show you. And it's a relatively long list. It has a few items, quite a few items. And you may guess that what I will show you right now in this hour are typical exam questions. Okay, in the first examination, normally I give you several systems, like 5 or 10 system relations, and at the right hand side I ask whether property A, property B, property C, whatever, the properties are valid or not, and you have to say yes or no. It's a yes no, a very small, compact, not a very classical way. It's like a test question. But you have to be careful about these things, so try to understand what I'm telling you now. The first property, so the title is System Properties. The first property of interest is memory. The system could be memoryless or with memory. Okay, there are two choices. It is either with memory or it's memoryless. Well, if in the relation of x of n to y of n, or x of t to y of t, it can be discrete time or continuous time, of course. In this relation, if the output only depends on the same time instance of the input, then the system is memoryless. There are many memoryless system types you can write. Most of the systems are with memory. For example, y of n is equal to 2 times x of n. An amplification. It's memoryless. Or y of n is equal to x squared. Let's give an example from continuous time now. Y of t is equal to x squared t. Please be accustomed to such a notation in functions. Whenever I say x squared of t, it means x of t in a big parenthesis squared. So as you see, y of t depends on the value of x of t at the same t only. This is also memoryless. Y of t is equal to 2x squared of t plus 5x of t plus 1, for example. This is also memoryless because it doesn't depend on the past or the future. By the way, the memory property is valid only for the current time instant. It's, even if it is related to the future time, it is still with memory. So this is memoryless. And then y of t is equal to x of t plus 1. As you see, the output requires the knowledge of a future sample of the input. So this one is with memory. Okay, that's what you have to say. Or y of n is equal to summation k from minus infinity to n x of k. What was this? Do you remember that? It's an accumulator. It is clearly with memory because it requires all the past information from minus infinity up to the current. So this is with memory. For the time being, in order to check for the existence of a property, whether it is memoryless or with memory, property, you have to have strong intuition. So try to solve the questions at the end of the chapter. At the end of the chapter, they ask whether this is memoryless, is it linear, is it time invariant, is it causal, is it stable. etc. Such properties we will see. Try to solve them. Usually the first initial questions are with answers at the back side. So check your answers, whether your intuition is correct or not. You can easily fall into a trap. Okay? It's very easy to make a mistake in such questions. So exercise is what I would suggest. You see, the accumulator is with memory. The way the capacitor works is also with memory, right? From circuits, that's one thing that we remember most. Capacitor has memory. And what is that memory? It accumulates the current. It integrates the current from minus infinity to the current time. So all the past current functions are integrated. That's why it has memory. It's similar to this summation. In that case, it is replaced with an integration. Now another property that requires some intuition again is invertibility. Is the system invertible or not? Usually the question goes on like this: is it invertible or not? And if it is invertible, what is the inverse? Okay. It's not an example. It's property number 2, of course. Now comes an example. Y of n is equal to 2x of n. An amplifier. Is it invertible or not? By inspection, of course, you can immediately find the inverse system. If you say z of n is equal to half of y of n, it will give you x of n. So the attenuation system, halving system, is the inverse system of double magnification system. So of course it is invertible. Let's put a check. It's invertible. But not all systems are as simple as this. For example, y of n is equal to 0. The system seems not to be connected to the inputs. Is it invertible? This is an easy question again. Is it? No, it's not. From 0 you cannot go back to the input because the input is not here anyway. It's gone. It's lost. If you lose the information from the input somehow, if you cannot resolve the input, of course it's not invertible. Let's see if we have any further examples, but we can construct some examples, of course. Y of t is equal to, for example, from minus infinity to t x of tau d tau. Is this system invertible? Can you tell me x of t from y of t? Can you construct a system which extracts the information of every time instance of x of t? The answer is yes, because in fact we have seen this inverse from the calculus, fundamental theorem of calculus. This is an accumulator, the integration, and the inverse system here is z of t is equal to the time derivative of y of t, and it will give you x of t. So the time derivative of the integral is the signal itself. See? Interestingly, that system is invertible, just like another invertible system of y of n, which is the accumulation k from minus infinity to n x of k. You accumulate the values of x of k from minus infinity to infinity to the current time instant n, and the way to extract the original information is z of n, or the inverse system is this: z of n is equal to y of n minus y of n minus 1. This is the inverse system, and it will give you x of n. So this is invertible. As you see, invertibility is a little bit tricky. Sometimes you feel like you're not able to find the inverse system immediately, but that doesn't mean that it's not invertible. Usually, students fall into a trap in solving questions regarding this invertible, non-invertible. But fortunately, it's not very important for us. Okay, so it's not the end of the life. There are other more important, more critical properties of systems, and as long as you can detect those things, you will still be safe. And yeah, the next property is causality. And this is one of the words where students fail to pronounce. I have seen several cases of casualty and things like that. Casualty is of course something else. This is causality. And the answer to this is the system is causal or non-causal. Causal, you may guess from the name what it means. Causality. It is because of the input. It means, does the output depend on the input? Or the input for now and the past. For example, an accumulation system is a causal system. Because, as I say, because. It is because of the input. The only thing that violates causality is a constant output, for example, violates causality because it's not because of the input, or if it depends on the future of the input, which didn't appear yet, then it is called a non-causal system. Non-causal systems cannot be physical. In physics, in mechanics, circuits, etc., you can never have non-causal systems because your system will never know the future of the input. The input hasn't arrived yet. It will arrive 10 seconds later. So your output shouldn't depend on that 10 seconds later input. If it depends on that, it becomes a non-causal system. What are the non-causal systems that you can think of? For example, I will try to construct non-causal example. Y of n is equal to x of n minus 2 plus x of n minus 1 plus x of n plus x of n plus 1 over 4. As you see, this is an averaging system. How can I get rid of this? Well, anyway, as you see, I'm now doomed because since I cannot get rid of this, okay. But now, how will I get rid of this thing? Okay, it's good. Sorry. Yeah. Now, this is such systems are called time averaging systems. It's averaging some portion of the data. 2 back, 1 back, current, and 1 future. It averages. It's like blurring the inputs, low pass filtering sort of. We will see that. And is it a causal system or not? And because of this n plus 1 term here, you see that for the evaluation of y of n, it requires 1 future sample. So this is non-causal. However, y of n is equal to k from minus m to 0 x of, okay, let's say 2 times x of n plus k. Okay, let's think of this system. Is this causal? It seems to be causal because it requires the summation of all the terms to x of n, which is okay. The current time is okay. X of n minus 1, x of n minus 2, x of n minus 3, up to x of n minus capital M. They are added up and doubled. So this kind of system is, as a matter of fact, causal. However, this thing wouldn't be causal. This example. Another averaging filter, but this time it's k from minus m to m, x of n minus k. It's averaging from the center point m to the left, m to the right, adding them up and dividing by 2m plus 1, which is taking the average of all the samples. For each n, if n is increased, the sliding window also increased. It shifts towards the right together with the input. But this one requires a future sample, or in fact m future samples. Therefore, it's not causal. So this is causal, this is non-causal. Now the next question, I'm not going to give you the answer, and I want you to think about it. Y of t is equal to x of t squared. Okay, is it causal? I will give you some further examples, and I will leave all of them unsolved. Y of n is equal to x of minus n. Is it causal or not? Probably you'll immediately have an idea about that, and probably it's correct, but you should do it by yourself. Another example. Y of n is equal to 1 over 2 to the power n plus 1 x cubed n minus 1. It's getting harder and harder. Is this causal or not? It depends on, this last example depends on a future value of n. There is an n plus 1 term. But you have to ask yourselves this question: does the output depend on a future value of the input? It's not n. N is not important. N is just a number. It is x of n that shouldn't be from the future. So does it depend on future input? The last one. Let's solve it. Let's give a name to that. That thing is causal. Okay, it's not non-causal. It is causal. Although there is an n plus 1 term here, it's not inside x. The future samples should be from the input for non-causal, and this is okay with that. So this is in fact causal thing, and try to understand why it is causal. It's a little bit complicated. Okay, what number are we at? It was 3. Let's proceed with 4. Stability. Is the system stable or unstable? That is the answer that you have to give. But of course, before that, you have to make a description of what we mean by stability. A stable system, according to the definition, must behave like this. If the input is bounded, if you know an upper bound of the system, the inputs, no matter how long a sequence or a function it can be an infinite length, the output should also be bounded with a certain bound. That is the stability definition that we will use, which is also known as bounded input, bounded output stability. This way to solve causality causal or not, and stability. The tools we don't have yet, so you have to use your inspections mostly. But in the future analysis of systems, in the next chapters, you will have the tools to immediately tell me whether this linear and time invariant system, they are only for linear and time invariant systems, by the way, is stable because this. You will see a property, or it is causal because of this. You will immediately tell me, but for the time being we don't have the tools yet, so you have to use your imagination and your inspection, intuition sometimes. So stability is bounded input, bounded output stability, also abbreviated as BIBO. And in the next semester, you will try to obtain controllers in control systems theory courses, which are bounded input, bounded output stable, BIBO stable. This is something that we will use a lot in the next semester. But what can you check for at least intuitively in order to answer some of the questions? For example, what can you say about this system? Y of n is equal to summation k from minus infinity to n x of k. What was that? It is an accumulator. We know it. Is it BIBO stable? Well, just think of one very simple example case. Suppose that x of n, the input signal, is all ones. 1, 1, 1, 1, 1. Is it bounded? Of course it is. It is bounded by 1. It never gets larger than 1 in value. Okay? If you accumulate all ones from minus infinity up to a certain point, what will you get? Infinity summation of 1, 1, 1, 1, 1, 1 plus 1 plus 1 plus 1. So the output grows indefinitely. And input is x of n is equal to 1, output y of n is equal to infinity. So it is unstable, you have to say, for this system. But another example, y of n is equal to x to the 100th of n. You are taking the 100th power of each term. Is it BIBO stable? And the answer to this is yes, it is. Because if x of n stays in a value, its 100th power will also stay in a value. It will be a very large value, okay. But it is still bounded. What is the bound? It is bounded by the maximum numbers 100th power. Or y of n is equal to k from minus 1 million to n, n minus 1 million, sorry, I should n minus 1 million to n x of k. Is this stable or not? It is averaging a lot of data, but still it's stable. If the input data is bounded, then summation of all those 1 million terms will still be stable or a finite value. It will not diverge anyway. So this is still a stable system. Unstable systems are a little bit tricky. They usually go without bound. Okay, you have to check that kind of a property. But we are just giving a glimpse anyway. So I tend to ask relatively easy to see cases in the examinations if we don't see the tools to see whether a system is stable, causal, etc. or not, because we don't have the tools yet. Okay, the next property, what's the number of that? 5. Okay. Property number 5 is time invariance. Is it time invariant? Is the system time invariant? or is it time varying? These are the two answers that you have to choose. Time invariance is an important thing. As I said, the others, for the time being, we don't have the tools, they are not very significant, etc. But time invariance is the thing that you can strictly detect for any kind of a system. If the output shifts the same amount that the input shifts. Okay, so suppose that you apply an input like this. At 0 and 1, it is 1, 1. This is x of n. And the output you observe is at minus 1 it is 1, at 0 it is 2, at 1 it is 3. Suppose this is the input-output relation of a system. If the system behaves like this, suppose that we shift the input to here, at 3 it is 1, and at 4 it is 1. What does it correspond to? It corresponds to a shift of the input to the right hand side by an amount of 3. Okay? The output should be shifted to the right by an amount of 3. Exactly the same. That means it is time invariant. So it must be like at 2 it is 1, at 3 it is 2, and at 4 it is 3. So if this input-output relation holds for any kind of a shift, of course, not only for a single case, for all shifts the input and output must slide simultaneously, then it is a time invariant system that we have. Okay, now let's try to see some examples. Y of n, my favorite example, k from minus infinity to n, x of k. Is this time invariant or not? And the answer is yes. Okay? It is time invariant. Just draw some x and draw the accumulation of that as an input-output relation. Then shift that x by some amount. You will see that the corresponding output y shape will also be shifted. For example, if you have an impulse in the center, then its accumulation will be a unit step function. If you have an impulse not at 0 but at 5, what will be the output of the system? It will be a unit step function starting at 5. So the output unit step function will also be shifted by 5. In fact, all the systems in discrete time or in continuous time that have a differential or a difference equation of this form. This is an integral equation, so it's a difference equation. What do we mean by that? A difference equation is like this. Y of n is equal to x of n plus a times x of n minus 1 plus b times x of n plus 1 plus c times x of n minus 2, and things like that. Okay, you add up several shifted versions of the input. This is a difference equation. In fact, you can also do the same at the output side as well. So this is time invariant. Or you can do it in the left-hand side of the equation as well. Like a times y of n minus 1 plus b times y of n plus c times y of n plus 1 is equal to d times x of n minus 1 plus e times x of n plus f times x of n plus 1. This is also a difference equation. And all such difference equation relations have time invariance. Okay, the amount of shift in the input will reflect to the amount of shift at the output. And this is also the same, valid, for differential equations too. So y double prime of t plus a y prime of t plus b y of t is equal to c x of t plus d x prime of t. This is a differential equation this time, right? And this differential equation input-output relation indicates a time invariant system again. How about this? Y of t is equal to x of t squared. Is it a time invariant system? If you don't have a differential or a difference equation, you have to check. And the way to check is quite easy. Apply a shift into the input time index and see if the same amount of shift reflects to the output. Suppose you have x of 2, at t is equal to 2, y of 2 is equal to x of 4, isn't it? Now let's take a look at t is equal to 4. At t is equal to 4, how much shift does it correspond to? It corresponds to a shift of 2. 2 plus 2 is 4. So we are now evaluating y of 4. How much shift does it correspond to in the input? X of 16. And the difference between 4 and 16 is 12. It's not 2. So the amount of shift at the input is not reflecting to the amount of shift at the output. It is not time invariant. It is time varying. The output depends on time. As a matter of fact, if t is in an awkward situation like t squared, or if t is at the outside of, not inside of x of t, like this, y of t is equal to t times x of t. This clearly depends on time, right? It is not time invariant. It varies with time. And can we see it rigorously? For example, let's take a look at y2. It is equal to 2 times x of 2. And then y4 is equal to 4 times x4. The difference between these two time output instances is just separated by 2. Now think of another case. Let's say y3 is equal to 3 times x of 3, whereas y5, again 2 shifted version of that, is equal to 5 times x of 5. So the scale is arbitrarily changing, and you have to know the time instant. You cannot just shift the input by some arbitrary amount. For example, instead of x of 3, if you want to find now x of 1, or if you want to find the output at x of 1, you shift the input by 2, x3 is shifted to x1, but this 3 scale changes. It's not 3 anymore, it has to become 1. So the output depends on time. It doesn't depend on the input only. By shifting the time, you are altering the output. In general, this is what you should get. Y t minus t0 must be a function of x of t minus t0 by an arbitrary change of t0 only. So if you have an output at a certain shift for a certain input, when you shift the input, the output should shift simultaneously, and this equation over there reflects that. If this equality doesn't hold, then you say that it is not time invariant, or in English it is time varying. This time invariance thing is quite important. Now I want to show you a few more examples. For example, y of t. Then tomorrow we will continue with the linearity property, the second important one. So the two important properties are linearity and time invariance. Okay, the others can be tolerated, but these two you have to understand quite well. Sine of x of t. Is this system time invariant? Yes, because it's just like the top one, right? The input changes and the output changes. If you say if you can write this, y of t minus t0 is equal to sine x of t minus t0, which is correct by changing t0 only. You immediately have the time invariance. So you put a check. Usually if you have a t, as I say, outside the function or somewhere, outside x of t, then it is a relation, it's a direct relation with t, so it becomes not time invariant, it becomes time varying then. Or if t is not in a linear form like t squared, square root of t, or sine of t. Y of t is equal to x of sine of t. Now this is clearly not time invariant, it's time varying, because you cannot say this. Y of t minus t0 is not equal to x of sine t minus t0. Because of this property, you say that this is time varying. For the future references, I have to confess that the thing that you have to keep in mind is that differential equation input-output relations or difference equation in discrete time all have time invariance, and they are the interesting class of systems that we have to learn and we have to elaborate. For the rest of the course, we will elaborate on differential equation type of input-output and difference equation type of input-output, and you will immediately say that, well, they are time invariant. Let's see now. Okay, now the last property and the most important again. Is it 6? Well, it's linearity, as I say. Is the system linear or non-linear? A linear system has two cases. Suppose that x of t goes into your system and y of t comes out. Let's call it x1 of t. x2 of t, when a different signal comes in, this is y1 of out, y1 of t at the output, goes into the system, and the output is this time y2 of t. Suppose you make these observations. Then your system must hold these two, or let's say A. Some constant c times x1 of t coming into the system must produce the same scaled version of the output. So when you double the input, the output must be doubled. When you halve the input, the output must be halved, etc. Okay. This is property part A. You have to check this for linearity. And part B is if you combine the inputs for a linear system, the outputs must also be combined. You have an output for this input, you have another output for another input, you add the two inputs, the outputs must be added. In fact, the combination of these can be reflected as follows. C1 scaled x1 of t plus C2 scaled x2 of t going into the system must produce C1 scaled y1 of t plus C2 scaled y2 of t. You can immediately check with this single formula too. Instead of A and B, just check this A plus B. But while checking these things, it's a better idea to check whether A and B both hold separately. I recommend to do them separately. Then you will see. Again, a rule of thumb, a very simple rule of thumb. If you have a differential equation or a difference equation, they are linear systems. Okay? You don't have to check them. The differential equations that I gave you as an example. A truly linear system, y of t is equal to 2x of t. If you scale the x by a, y will also be scaled by a. And if you have two separate signals, if you combine them, because of the parentheses, both of them will be twice of the input, and the summation will be twice of the summation. So this is trivial. A very easy case. And a very counterintuitive example is coming here. Y of n is equal to 2x of n plus 3. Is it linear or not? By the way, the input-output relation draws a line, as you see, so it looks very linear. Y versus x. It looks linear. Just check condition A. Scale the input by 2. Is the output scaled by 2? No. The output is scaled by 2 for example, 4xn plus 6, not plus 3. So part A doesn't hold over there. This is nonlinear, interestingly. A nonlinear system, again, another easy way to check nonlinearity. If the input-output relation doesn't pass through the origin, then it's nonlinear. A linear system must have 0 input, 0 output condition. It must pass from the origin. If it doesn't, from A, it doesn't hold. Therefore, we have to say that it's a nonlinear system. We all understand that. So in the differential equations, if there is an additional constant, plus 3 or something, in either side of the equation, then 0 input, 0 output condition doesn't hold. It doesn't pass from the origin. And it becomes nonlinear. But linearity is important. We will have to see a lot more examples. So let me stop at this point. Next week, we will continue a lot with these things.